What's up, my favorite people? If you're watching this, then it should be Tuesday, April 6th. And I think I messed up the date on the last screencast because there was a day off last week, which was awesome. But today should be Tuesday, April 6th, and we're going to talk about the law of conservation of energy. So we're going to move into the 7.3 today. Now, last time I saw you, we were wrapping up 7.2, and I wanted us to be able to compare and contrast calories and generally explain how a can calorimeter works using that equation right there. We went over all of that yesterday, and then we did a Google form. So if you haven't done those assignments, you're going to need to catch up. We're moving ahead in the science this week. But at the core of it, we looked at this video right here. And basically what happens is you take any object and you can set it on fire, especially food. Food has calories within it. It has energy within it. As that food piece burns, it's going to release that energy, which is an oversimplification of the process of digestion. Digestion doesn't involve burning of food, it involves breaking down of food. But as that food gets broken down, either using your digestive enzymes and your stomach acid, which is acidic, or by using fire, at the end of the day, what we're doing is we're breaking bonds. And when we break the chemical bonds in the food, it releases energy. It releases that energy in the form of heat, but in our system, it releases the energy in the form of chemical energy, and that energy is then used throughout our body. We can measure the energy using that equation, Q equals mc delta T. Here it is right here, Q equals mc delta T, where M is the mass of the water. So when we use a calorimeter, we'll always change the water. We'll take the energy from one thing and use it to heat up water. So M is the mass of water, T is the temperature in degrees Celsius, and it's delta T. Delta T means final minus initial. So you'll take the final temperature of the water and you'll subtract the initial temperature of the water, whatever the water was at. Q is energy, which we measure in calories. So Q is a measure of calories, and that's little c calories. And then C is a constant. It's called specific heat. And it tells you how much heat you need to increase the temperature of a substance. Specifically, this case, we'll deal with water. The specific heat of water is always 1. It's a constant. But the specific heat varies for every substance and actually every phase. Water that's frozen into ice has a different specific heat than, say, water that's been boiled into a gas. So C is a constant. It's the amount of heat required to increase the temperature of a substance. But for water, it's 1. Though moving forward, we won't always use water. Though when we use the type of calorimeter that we were just talking about, a can calorimeter, we will always be talking about water. I know this slide is from yesterday, but make sure you get down the important stuff in your guided notes again. What are these variables? Because we're going to be doing a practice problem, not just today in the screencast, but we're actually doing an activity today. So you need to know these things. So Q equals mc delta T is a really important equation that lets us solve for energy within a substance. We can figure out how much energy that water gains. But what we're going to talk about today is the law of conservation of energy. It's a little bit more complicated than that because if water's gaining energy, we're going to get Q that's positive. But Q doesn't have to be positive. Q can be negative. Q or energy is negative when energy is given off. When we break those bonds, Q is negative. And when energy is absorbed, Q is positive. So we're going to define the law of conservation of energy and then solve for Q, energy, M, mass, or C, that specific heat constant, which for water is always 1, but we can solve for it if it's unknown in a calorimetry problem. This is where we will be all week. So what is the law of conservation of energy? Well, we've talked about the law of conservation of matter, which says mass can't be created or destroyed. But conservation means can't be created, can't be destroyed. And so that's the same thing with energy. The law of conservation of energy says that energy cannot be created and it cannot be destroyed. Make sure you have that definition in your guided notes. So if it can't be created or it can't be destroyed, what it means is that energy is converted from one form to another form. And this might be a little bit complicated, but basically the amount of energy is always constant. So when you say burn something, the energy that is within that substance, it has to go somewhere. And some of that energy is going to go into the water, but some of that energy is not going to go into the water and it's going to spill outwards. If you are having a bad day and you eat a candy bar because you deserve it, that candy bar still has calories. Like the calories exist. And when you put those calories into your body absorbs those calories. There's really nowhere else for those calories to go. And this is called the law of conservation of energy. So if you know how many calories your body needs to function, approximately, and you're eating approximately that many calories, then you're going to be in energy balance. You're not going to see your weight go up or go down. If your weight has steadily been going down, well, what's happening is that your body doesn't have as many calories as it needs. You're not giving your body enough energy. So if you give it more energy, because energy can't be created or destroyed, like if you're just not giving it enough energy, then your body has to use its own energy sources. Now we can represent this algebraically or mathematically using this equation right here. Q of object 1 equals negative Q of object 2. So Q, remember, is calories or energy. And so what we're saying is that energy absorbed, positive Q, is equals to energy given off. So when you eat a candy bar, your body absorbs that energy. You're getting positive energy coming from that. But the food is giving off energy. If you were to use Q equals MC delta T for the food, it would come out to be a negative value because energy is given off. So Q1 equals negative Q2. Well, what that positive Q means that energy is being absorbed, and negative Q means that energy is being released. And that third bullet point that I'm looking for in your guided notes is to say that the energy lost by one substance has to be gained by the other substance. So if you eat something, the food is going to give off that energy, negative Q, and your body is going to absorb that energy. Because of the law of conservation of energy, energy can't be created or destroyed, but it can be converted from one form to another. Do we have all of that in our guided notes? Because this is really critical. We're going to try a practice problem. Okay, I just had a little glitch with my technology. So we're going to do a practice problem. And we have a piece of food being burned in a calorimeter, causing the water to increase in temperature. This is exactly what we're doing with our little lab simulation today. So make sure you're paying attention. So we have a piece of food that's burned, and the mass of the food doesn't matter yet. We'll come back to that tomorrow. Causing 50 grams of water, so that's the mass of water, to increase its temperature by 35 degrees. So that's delta T. Delta is the change in. And since the temperature is changing by 35 degrees, that's telling us that the initial water is irrelevant and the final temperature of the water is irrelevant, but the temperature changed 35 degrees. What we're solving for, how many calories? Well, remember, calories are a measure of Q. We want to know how many calories were in the food. And in order to solve for the Q, we need to use that really important equation, Q equals MC delta T. But what was C again? C is called the specific heat, and it's a constant. It's known for almost every substance at this point. And for water, since we're talking about water, the C of water is always 1. So we can just plug in here. The mass is 50, the C is 1, and the change of temperature is 35. I'd like you to put units in your work because then we can cancel out units. Look, grams cancels out with grams, as does degrees Celsius and degrees Celsius. So we're left with just calories. Now, these are science calories, but we're solving for Q, which is a measure of energy, and we'll get out calories. When I did this math, I got out 1,750 calories, which is exactly what you would get if you plugged into this equation right here. Now, you would think that's the end of the problem. 1,750 calories is a lot, but notice we're asking about food calories. Food calories, dietary calories, and science calories, little c versus big C, are slightly different. Do you remember the conversion factor between food calories and science calories? Sometimes food labels are called kilocalories, kilo meaning 1,000. When we do our scientific calculations, we're always going to get out these little baby science calories. And when we're eating food, we always measure them in dietary calories, which are capital calories. We went over this yesterday. That's because keeping track of 2,000 dietary calories is a lot easier than keeping track of 2 million science calories that you have to eat in a day. And so the last thing I'd have to do is convert my science calories into food calories. Well, this right here is it's an equivalency statement. They're equal to each other, which means I can write 2 conversion factors from this. I just wrote them both out here in blue. These would both be conversion factors. And which one do I want to use? Well, I'd have to figure that out by setting up my conversion down below. To remind you, in the top left, we always put the given. It's what we have and it's what we want to get rid of, which is science calories, 1,750 calories. Now, whatever units are up here, science calories also need to go down here so that they can cancel out. And I'm writing cal, but it just means calories. And what I want are dietary calories, capital C calories. So which conversion factor do we want to use? We need dietary calories on the top. So we want to use the one I outlined in green. For every 1 food calorie, for every 1 dietary calorie, there's 1,000 science calories. And so we'll take 1750 and multiply it by 1 and divide it by 1,000. And when you do that, you get 1.75 dietary calories because science calories cancels out. And so just remember that when we're solving, we'll always get these little science calories right here. But usually what we want when we're talking about nutrition are dietary calories, or, food calories, as I'll sometimes call them. I went over all of this because we're actually doing an activity with this. And typically I'd split up the screencast, but a lot of people aren't watching the guided notes. So I'm going to explain the activity we're doing right now as well. So we're not going to do any more guided notes. We're going to talk about the activity for the day. Assigned in Google Classroom is this activity right here, the CAN Calorimetry Virtual Lab. So what we're talking about is a CAN calorimeter, where we will burn a piece of food and that energy will be absorbed by the water in the can. In order to watch the procedure for this, you need to be watching this screencast right now. So good for you. Typically, we would actually do this lab where we would have a soda can and we would burn a chip, and the chip would be on some kind of plate because it produces a lot of grease. It absolutely does. As that chip, or this is a Cheeto, as that burns, it'll increase the temperature in a soda can. That soda can is just suspended by using a metal stirring rod, and there's the thermometer in there. We would just use a regular thermometer, but this one's a little bit fancier. It's got a digital thermometer. Before I go on, I need you to pause me and open up the activity for today, the CAN Calorimetry Virtual Lab. It's the 7.2.2 assignment. It's posted in the classroom for today, April the 6th. Now, if we were doing this in real life, we'd have to collect some data. In order to find the energy absorbed by the water, we would need to find the mass of the water, right? So what we would do is we would take an empty soda can, it weighs 13.65, and then we would put some water in there. So the first thing you need is the mass of the water, which isn't going to change. So find just the mass of the water, subtract these, and get it in your data table. Then what we would do is we would literally just set that on fire. So I have a video here of this happening, and we're going to watch it a little bit faster than it needs to. So we would have had to mask this chip before. I'll give you that data point. And then once we set the chip on fire, so what we're doing is we're breaking bonds in that chip. And when we break bonds, it gives off energy. And where's that energy going? Well, some of the energy is going right to the can. And that can is absorbing water. And you can see that because the temperature of the water is heating up. We want to record the highest temperature that we see. Now, not all of that energy is going into the can. I mean, if you put your hands around that, you would feel the heat just distributing. And you can see this can is turning black. It's reacting. So not all of the energy is being sent into the can, but most of the energy is. And we want to record the highest temperature that we see. This will be our final temperature. 40.9, 41, 41. Okay, that's our final temperature. And I didn't record the volume of the temperature of the water to begin with. So let me stop this video. The initial temperature of the water before we set it on fire was 20.6. So the initial temperature of water is 20.6, and the final temperature of water is 41, I think is what we said. So with that, we have enough information to find out how much energy the water absorbed. We know the mass of the water. We know the specific heat of water. It's 1. It's a constant. And we know the initial and final temperature of water. But you may notice that there's still some food here. We didn't burn all of it. And so what also we have to do is take a look at how much food did we start with and how much food did we end with, because we haven't used up all of it. When you eat food, all of it gets used up. Oh. So the mass of the food before, so that's the food and the watch glass. In this case, it's more like a holder. But so we have the mass of the food before, and then we have the mass of the food after. So you can see that actually a significant amount of this food didn't get burned. And there's a part of the chip right there that hasn't even been reacted at all. If you were to eat that chip, all of the chip would be reacted. So we're actually not burning that much food here. We need the mass of the food before, 10.9, and then we need the mass of the food after, 9.6. And then I'm just going to run through this so you don't have questions. So we have the initial mass of the water. You subtracted those two amounts, and you have the initial temperature and the final temperature of water. And we just got the initial mass of the food and the final mass of the food. So we should have this whole thing filled out. The first thing that we're going to do is find out how much energy is absorbed by the water. As I said, we know the mass of the water. You have it right here. The specific heat of water is 1, and the change of temperature of water, you'll look at the final and the initial temperatures. I have you do it in question 1 right here. That's going to give you energy in science calories. And question 4 then has us convert from science calories into food calories. There's 1,000 science calories in a food calorie. But importantly, we can use the law of conservation of energy to say, well, if the water's absorbing this amount of energy, that means the food is giving off this amount of energy. Q of water equals negative Q of food. So if the Q of water comes out to be positive, if the water absorbs energy, where does it get that energy from? It gets it from the food. So we'll be able to figure out how much energy comes from the food. But again, remember, in question 5, we didn't react all of that food. There was still some food left over. And so what we'll be able to do in question 6 is figure out how many calories are in a gram of that food. So you'll take the amount of calories in your food, Q of food, and divide it by how much food was burned in order to figure out how many calories per gram there were. Then you'll do a little claim, evidence, and reasoning to think about, well, if there's supposed to be 5 calories per gram in chips, why did the number that we get, why is it less than that? And it should be less than that. So yeah, do this claim, evidence, and reasoning. But at the core, what it comes down to is using this equation right here to figure out how much energy is absorbed by the water, finding the Q of water, and then using this equation right here to say, okay, well, if the water absorbs this amount of energy, this amount of calories, then how many calories were in that food, the amount of food that we burned. And if you have any questions, let me know. I'm here to help. I appreciate you watching, and I'll see you next time.